So today I'm going to walk you through how I rebuild these Ray-Ban sunglasses with the help of 3D scanning, reverse engineering, and 3D printing. Here's the original pair of Ray-Ban sunglasses that I will be recreating. The frame's geometry is pretty tricky to reverse. It's full of complex curves across all three planes. This frame is made entirely from acetal, no steel wire reinforcement at all. In this video, I'm skipping the hinge design. It's tough to swap out a steel hinge for a plastic one while keeping the same stiffness. By the way, steel hinges for glasses are available on AliExpress if you need them. Since I'm printing the frame with a standard resin, it's going to be stiffer than acetal, which means the lens might not snap in easily. A tougher resin with more elasticity would probably work better for this project, but I don't have any on hand to test. Alright, we will start with 3D scanning, and for this project I'm using the Creality Sermoon X1. Since the frame is translucent and super refractive, I need to spray it with developer spray SKDS2 to get a clean scan. I'm scanning at 0.15mm resolution using the 7-line laser mode. Since the glasses frame has such a narrow surface, you need to watch the green laser line on the preview screen to keep the working distance right. When flipping the frame to scan the other side, you have got to be really careful. It flexes easily and the side pieces need to stay in position. After flipping, the side pieces shift a little, but there is not much I can do. When I merge the scan, some overlap might show up. Next up is post-processing. I will fuse the point cloud at 0.15mm and Creality Scan 4.1.7 has a new single body selection tool that makes isolating the scan data super fast. Since the frame has so many curves, I can actually align it automatically with just 2 scans. Next, I'm going to mesh the aligned data using about 1.6 million triangles. Here's the result. You can spot some seam lines where the side pieces shift during the flip, but I don't think that will be a problem once I reverse the side pieces in CAD. Okay, just a quick side note, this video is purely educational. I'm not suggesting it's a good idea to copy a patented product. I only want to show how reverse engineering works on a complex object. Here is another use case for scanning glasses without reverse engineering. You can actually try fitting them on a face. Like with the scan I made of my older daughter. You can see the nose pads touching her nose, but the lower part of the frame also rests on her cheek, so the integrated nose pieces aren't a perfect fit for her face. Since this frame doesn't have adjustable nose pads, it ends up sitting a bit too low on her face. Now I will explain the process I will use to reverse this frame in CAD. I will sketch 2D cross sections along the white lines, then use 3D sketches as rails to guide the curves along the frame's length. Some parts can't be modeled with the loft command, like the tri-junctions near the center of the frame and where the side pieces connect. In this area, I will model with 2D sketches and 3D sketches, then use the patch surface command to stitch everything together and turn it into a solid. Since the frame is symmetrical, I will just model the left side and then mirror it over to the right. I will model the side pieces separately, starting with 2D cross sections along the white lines and lofting them into shape. At the very tip, I will switch to 3D sketches and patch surface command to finish it off. I have imported the scan point cloud into AutoDesk Inventor, and I will use it to demonstrate the CAD modeling process. You can see the scan data is sharp and clean with no noticeable noise. Every detail is captured, even the groove where the lens sits. This Ray-Ban frame is really complex with lots of curvature changes across different planes. Much more intricate than the ordinary glasses I have reversed before. First, I slice the point cloud into a thin 0.5mm section and create 2D sketches shown in the yellow. The magenta lines are 3D spines, which I use as rails to control the loft surface. This is the tri-junction area where I need 3 2D sketches and 3D splines to define the patch surface boundary. After patching the surfaces, I use the stitch command to join them together and turn the model into a solid body. From the tri-junction to the mirror plane, I use another 2D sketch to loft the body. Here is another tri-junction near the side pieces, where I use 3 2D sketches and 3D splines to define the patch surface boundary. Next, I create 3D splines to connect the tri-junction bodies to the first lofted body, and then use the loft command to join all 3 together. Next, I sketch on the side pieces contact face and loft a body that connects to the tri-junction. Next, I make a 2D cross-section sketch and connect it with 3D splines. Each spline uses 2 or 3 control points, which I adjust with the mouse until the curve matches the point cloud surface. The key to reverse engineering is using the scan data only as a reference for building 2D or 3D sketches. CAD works by turning sketches into 3D models. I don't use mesh for reverse engineering in CAD because it makes it harder to align 3D splines accurately to the surface, and you lose precision when tracing cross sections. You can see here that the 3D splines match the point cloud surface perfectly. You might wonder how many 3D splines are needed to control the surface shape. The truth is, you just have to experiment a bit. After a few tries, you know exactly where to place them. On the first trial, you can place the splines at the joints of the 2D sketch. Adding too many splines doesn't necessarily mean better practice. Okay, here is the final lofted body. Remember, CAD builds 3D models from sketches, and those sketches can always be adjusted later. If the surface doesn't look right, you can tweak it anytime. unlike polygon modeling tools where you are stuck with just the undo button. I'm not making a plastic foldable hinge. It would have to be huge to match the stiffness of a steel hinge. Instead, I will make a 3mm key that slots into the side pieces and glue it with a plastic adhesive. Next, I will mirror all the executed commands to the other side using the YZ plane. So now the main body of the sunglasses is complete. Next, I will start modeling the side pieces as a separate part. The side pieces are easier to model since they don't have any tri-junctions. All you need is a 2D cross-section sketch placed in the light spot, usually just before the shape starts to change. Most of the 3D splines here only need 1 or 2 control points. A few use 3. If you find yourself needing more than 3, it usually means your cross sections are spaced too far apart. At the end of the side piece, I create a capsule shape using 3D sketches and then use it as the boundary for a surface patch. For the final step, I extrude a rectangular slot to attach the side piece to the main frame, and I also add a small hole cutout to prevent suction when printing with the resin. Then I mirror the side piece over the other side. And that's it. The modeling is done. Here is a tip. Use the loft command whenever possible. It is the fastest way to build complex 3D shapes. For areas that are too tricky, like the tri-junctions or the tip of the side piece, switch to the patch surface command. It's slower, but it gives you a precise control over any shape. Finally, remember this: any object designed in CAD must also be reversed in CAD. There is no shortcut or workaround. Next up is resin printing, and for that I'm using Sheet2Box, the slicer made for resin printers. Sheet2Box has a smart auto orientation tool that optimizes supports and helps reduce print failures. The medium supports look a bit skinny to me, and since this is a long print, I will go with heavy supports. If the print fails, the real cost isn't the resin, it's the reprinting time. The drawback of heavy supports is that they are harder to remove and leave larger dimples, which take more effort to sand out. This print will take over 8 hours, and honestly, there is no way to get a usable glasses frame with an FDM printer. I'm printing this with the Phrozen Sonic 16K using high-profile standard resin. It prints at 20 microns on the XY plane and 50 microns layer height. So that's about 4 times higher resolution than an FDM printer. Most people think resin printers are just for toy figures, but that's not true. I have used them plenty of times to print functional parts with ABS-like resin. Resin printing relies on suction to hold the part to the build plate. To remove it, just pry gently at the edge and it will pop right off. I set the clearance at 0.1 mm for the side pieces key, so it fits snugly without needing any adhesive. And here's the print result. You can see a few dimples left from removing the supports. If I had rigs using medium supports instead of heavy ones, there would have been fewer marks. But since I'm using standard resin, sanding out those supports dimples is pretty easy. The print come out with high precision, no noticeable deformation or distortion even on this thin glasses frame. When comparing elasticity, I found the Ray-Ban frame made from acetal is much more flexible than the frozen hyperfine standard resin. So when I try fitting the lens into the printed frame, the profile matched, but the frame was too rigid and the lens wouldn't pop in. But if I switch to a higher elastic resin, what they call a tough resin, I think the lens will fit. I could try pushing harder, but I'm worried that the frame might break. Unlike the original acetal frame, the lens just pops right in with a firm push. I'm happy with how the print turned out. I probably get some steel hinges, add mounting points and reprint it using tougher resin. I can barely notice any geometric differences between the printed frame and the original one. As I mentioned earlier, please avoid replicating any patented components. This video is intended solely for educational purpose. Thanks you guys for watching. I'll see you in the next video.